A pulsar. A pulsar is a pulsating radio star. Pulsar is abbreviation of pulsating radio star. The watches came later, as did all the other things that are called pulsars these days. These pulsating radio stars turn out to be incredibly small. They're about 10 miles across, but they're also incredibly heavy. If I can count on my fingers, they weigh 1,000 million tons. And if you put all those millions of tons in a ball 10 miles across, its density is like the density of the nucleus of the atom. That's a bit hard to comprehend, and one way I have of explaining this is take a thimble, a sewing thimble. Take the population of the globe, 7 billion people, cram them one by one into the thimble, and when you have 7 billion people crammed in this thimble, it weighs the same as if it was made of pulsar material. They are amazingly dense. And because they're so dense, they've got some fascinating physics. It seems that at the end of its life, a really big star, much bigger than our sun, explodes catastrophically. And in the explosion, the core gets collapsed. So it was yay big, and it gets squeezed down to about 10 miles across. And it's spinning very, very rapidly. It's got a big magnetic field, and a beam of radio waves comes out. And it sweeps this beam around the sky, a bit like a lighthouse sweeping a beam of light. And every time the beam comes past the Earth, you get pulse, 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 very, very regularly. So it appears pulsing. It's actually a continuous beam, but it just sweeps across and gives a pulse, a flash, like a lighthouse. They're also sometimes called neutron stars because they're rich in some of the particles that make up the nucleus of the atom that we call neutrons. And because they're very, very dense, the physics inside these pulsars or neutron stars is utterly amazing. And a lot of it is not yet understood because in the very middle they are so extremely dense that it's way beyond where we've got data. So we're guesstimating. They've also got very strong gravity. They spin very fast. They've got large magnetic fields. They're strong and extreme in many, many respects. And so the physics of a pulsar, the physics of a neutron star, is really hard but fascinating stuff. People have asked, was it exciting finding the first pulsar? And the answer is no. It was worrying because the signal was so crazy, so extreme, so outrageous. Couldn't make sense of it. And you have to start by assuming there's something wrong with the equipment or something wrong. And we spent about a month checking things out, one after the other. The bit that really scared me was the telescope wrongly wired, because I had wired up the telescope, but it wasn't, it was okay. For example, we got another radio telescope with its own radio receiver, and they picked it up as well. So it wasn't a crazy signal that was fabricated by my equipment. But we had a lot of things to very, very carefully check out because it was very hard to understand what the signal was. The pulses were quite rapid, which means that the object emitting them is quite small. But the pulses also kept very, very accurate beat, didn't get tired. And this went on for a month at least, which means they've got great reserves of energy, so they're big. So they're small and they're big. Yeah, okay, what are we talking about? There were a lot of very puzzling things to sort out. And we were just beginning to establish a few of these things when I found the second one. And that was the exciting moment, because I knew it wasn't a fault with the equipment, that it wasn't interference, that it wasn't a satellite, it wasn't this, it wasn't that. and it really begins to look like some amazing new kind of star. And then a few weeks after that, I found the third and the fourth, and that really shouts at you, this is a new kind of star. Okay, it's an utterly crazy kind of star which nobody has believed could exist or do this kind of behavior, but it's some kind of star. Phew. So I found the first 4 pulsars, and we now know of about 2,500. They're quite hard to pick up because they're weak. We can see the ones in the near half of our galaxy, but we reckon we're missing a lot in the far half of the galaxy, for example. They're that weak. The next generation of radio telescopes will be an improvement. They all seem to be these spinning stars that are sweeping a beam around the sky. We can see that their periods are incredibly accurate, although if you measure to enough detail, we find that they're slowing up. The typical pulsar has slowed up by 1 second since the age of the dinosaurs. They're really good clocks. And this means nature has provided us with really good clocks dotted around the galaxy. And for the first time, we can use these clocks to test Einstein's theories of relativity. And we are doing so. And I have to say that so far, Einstein's theory of general relativity is looking pretty good. We cannot see any deviation from Einstein's theory bigger than 0.02%, 0.02%. But we're not stopping yet. We're going to hammer it a bit harder and see if we can find some deviation. They're also interesting objects because of the solid state physics. Very solid, very dense, because of the area around the pulsar, and because, like a lighthouse, each pulsar has its own characteristic pattern of flashes. We can probably use them as navigation beacons when we travel through the galaxy in spacecraft, spaceships. And there are just now a couple of spacecraft being sent up to do the first tests to see if they can pick up pulsars and get a fix on their position. So they could be navigation beacons for interstellar travel.